Suppose we have a conducting metal bar uh, in a region of external magnetic field, a uniform B field, and we give that bar a push to the right. And suppose it's resting on some conducting rails, these black lines here, sort of a conducting wire rail, frictionless for it to slide along. And we note that there's a loop here, a complete conducting loop that could potentially support a circuit. So I'd like to use Faraday's law to find the induced current in this loop here due to the changing magnetic flux through this loop. And that flux will be changing through the loop because the area of the loop will be changing. As the bar slides to the right, the area here will be increasing, which will lead to an increasing magnetic flux. Okay, so let's start by drawing a Faradian loop. Let's see, let's have our loop just sort of run around what we see here could potentially be a circuit. So through this conducting bar and along this conducting wire here, that's our Faradian loop. And we use right-hand rule to get our dA vectors. Let's have our dAs pointing out of the page, so they're parallel to our B field pointing out of the page. Get that to agree with our ds vectors, which will go counterclockwise. So dA and ds agree by right-hand rule. So counterclockwise will be our positive direction around this Faradian loop. Step 2, compute the magnetic flux through this loop, B dot dA through this here. Okay, well, I can break up that area into two parts. The area of this rectangle here, where there is no magnetic field. Our B field is confined to just the region from this point rightward. So in this area, there's no magnetic field, so no magnetic flux through that part. In this region, on the right-hand part of our big rectangle, there is magnetic field, a uniform magnetic field here. So uniform B there, and the flux through this part of our Amperian loop will be the magnetic field strength here times the area of this part. So that area is this dimension, which we'll call x, which will be a function of time as our bar slides to the right. So as the bar slides, x will get longer and longer. There'll be a bigger and bigger region of our Amperian loop that's in the field. So x times the length L here will be the area of this rectangle. So L times x, that's our area. Thus we come up L times x here, that's our area. So we come up with this expression for the magnetic flux at a particular moment in time through this Faradian loop. Note that B is constant with time, B is uniform, but it's x that's changing. It's the area of our loop that's changing as our bar moves further and further to the right. So here we are going to get a changing magnetic flux, even though we have a constant and uniform magnetic field. So that brings us to step 3, compute the rate of change of this magnetic flux. So d phi dt. So we need the time derivative of this. B and L are constant with respect to time, but it's x that's changing with time since our bar is sliding right. So ddt of this expression, B and L come out. We just need dx dt, the rate of change of x. But by definition, that's exactly equal to the x component of the velocity of the bar that is sliding on these frictionless rails to the right. These are our rails here and there. So Vx, that's dx dt right here. So we get this expression, B times L times V, for the rate of change of the magnetic flux. So as long as the bar is moving, as long as V is non-zero, the flux is changing. And a changing flux we know will induce an electric field, which will induce an EMF around this loop, which will induce a current around this loop. All comes from this changing flux. Time to apply Faraday's law, step 4. we state that our induced EMF as a function of time around this loop is equal to the induced current around that loop times the resistance of that loop. Say there's some resistor over here that represents the total resistance of this whole path. So I times R equals the opposite of the time derivative of that flux. So that's the opposite of this expression, BLV. And note, this BLV, this is exactly the same expression as we came up with from our considerations of motional EMF. Going back here, the motional EMF that we found developed across a conducting bar moving through a magnetic field after it was given a push, motional EMF was VBL, which is what we have here, VBL. Now, we came up with this without any kind of Faraday's law considerations at all. We didn't discuss induction to come up with this. We came up with this just from thinking about magnetic forces and electric forces and this expression here. So it appears we're reaching the same conclusion from two different perspectives, that in a situation like this with a moving bar through a uniform magnetic field, we will get an EMF across that bar that will drive a current if that bar is connected to a complete loop. What this is suggesting here, the fact that we arrived at this result for the EMF from two different lines of argument, is that there is some deeper connection between these two lines of argument. That Faraday's law is saying that there's some connection between electric forces and magnetic fields that is perhaps deeper than we see at first. It's suggesting, hinting at what Einstein's theory of special relativity suggests about electric and magnetic fields. That in fact, an electric field is what happens when you transform a magnetic field from a different reference point, and vice versa. So that's all we'll say on that for now. Let's just note that you can arrive at this expression for the EMF around this loop either from the Faraday's law argument, this argument here about the changing flux, or from our motional EMF argument. We end up with the same expression for this EMF. And so then that EMF equals our induced current times the resistance. So our induced current is given by this expression here. Just take that BLV and divide by the resistance to get this. And so we see that as long as the bar is moving, there will be a current driven through this loop here. And in fact, if that velocity is a function of time, then that induced current would be a function of time as well. However, if you were to pull that bar at a constant velocity, sort of just grab it and drag it at a constant velocity, we see that would induce a constant current in this loop here. Okay, about the sign, regarding the sign of that current, or the sign here, we see that if V is positive, the negative suggests that I would be negative. Let's check out what that means. So if Vx is positive, so if Vx is this direction, our equation suggests that I would be negative. And recall that negative I means that I is opposite the direction of our ds vectors. So it implies that the induced current that we're getting would be clockwise through this loop. If V is that direction, then our current induced is going to be clockwise, opposite the direction of our ds vectors. That's what we mean when we say that this current is negative. So let's just check Lenz's law to make sure that a clockwise current makes sense here. If our loop is getting bigger, then we have an outward magnetic flux through the loop. And as that area increases, we're getting more and more B field coming out through the loop. So we've got an outward magnetic flux that's increasing with time. We're getting more and more magnetic flux outwards as this area gets bigger. So the inertia, the electromagnetic inertia in our system will respond in such a way to try and reduce that outward magnetic flux that's increasing as the area gets bigger. So we can create that. We can create an induced current that generates a magnetic field that opposes that change. So what we need is B field into the page to oppose that increasing flux out of the page. So we'll get a B field into the page if we have a clockwise current here, creating B field inwards. So there we go. Lenz's law agrees with a clockwise current being induced by this bar moving to the right. That's the significance of this minus sign here. Note also it suggests that if our bar moves to the left, if Vx was negative, then if this was negative, then negative would mean our current was positive. It suggests that if the bar was moving left, our current would reverse and go counterclockwise instead, which also agrees with Lenz's law. If this bar was moving left, then the magnetic flux out of the page would be decreasing as this area got smaller. So we would need to add more flux out of the page to replace it. Therefore, we would need a counterclockwise current to add flux out of the page to try and maintain the flux that was originally there. So this expression applies whether the bar is moving to the left or to the right.